Everybody, welcome to my presentation. My name is Tiana Lowe, and I will be presenting nuclear energy with the focus of breeder reactions and the Fukushima nuclear power plant disaster that happened in 2011. So my goal is to offer a balanced perspective on whether nuclear energy is a responsible and worthwhile option for our future while discussing out these two issues that were assigned. As nuclear energy isn't a widely known topic, I just wanted to include some stereotypes that came to my mind, that came to some other people's minds when I asked them, what do you know about nuclear energy? What can you picture in your mind? These pictures are just some pictures that I assembled from what they were describing to me. So when I first was assigned this topic, my immediate thought, besides the stereotypes, was where is uranium from? What shape, what form does it come in? Where do we get it from? Where in Canada do we get it from? So, much of the world's highest grade uranium is found in northern Saskatchewan, particularly in the Athabasca Basin. Exploration for these deposits historically involved aerial surveys equipped with Geiger counters to detect radiation from the air. Once extracted from the ground, uranium ore goes through a process called milling, where it can be refined into small ceramic fuel pellets. Fun fact, these 20-gram fuel pellets contain the same amount of energy as 400 grams of coal or 410 liters of oil. The remarkable energy density is one of the reasons nuclear energy is considered efficient and long-lasting. All right, so topic 1, the breeder reactions. This works because of nuclear fission reactions. So nuclear energy begins with a process called fission. When a neutron strikes a U-235 atom, the nucleus splits into smaller parts, releasing energy in the form of heat, as well as additional neutrons. These neutrons can strike other U-235 atoms, creating a controlled chain reaction. The heat produced is used to convert water into steam, which turns turbines to generate electricity. The scientific process is the foundation of all nuclear power generation. All right, we have the reactor itself. So this part looks similar to regular nuclear reactors. However, there's a little bit of difference. Start with the fuel in the core undergoes the fission, which is the reaction we saw on the previous slide. It takes place in the core. This releases heat. There's also control rods in the large vessel here that regulates the reaction, and liquid sodium is pumped through, which absorbs heat from the core. This heat is given off by the continuation of the breeder reactions, so it is very important that there is a substance flowing through to cool things down. The hot sodium flows to a heat exchanger where it heats a secondary sodium circuit. The second loop makes steam, spins a turbine, turns a generator, and then produces electricity. So this is just like any other normal nuclear plant. However, liquid sodium is used as a coolant. As you see with CANDU reactors, maybe some other students will talk about CANDU reactors, deuterium or heavy water is used as the coolant or the moderator in that case. So what distinguishes breeder reactions from other nuclear reactions is the ability for it to use fertile materials such as uranium-238 or thorium-232 that are not themselves fissile, but when exposed to high neutron flux, converts into fissile isotopes, for example, plutonium-239 or uranium-233. This means a breeder reaction can produce more fissile materials than it consumes, effectively breeding fuel. All right, here's a little bit of reality of what can happen. This is the Fukushima disaster. So on March 11th, 2011, Japan faced one of the worst nuclear disasters in history at the Fukushima nuclear power plant. Even years later, 50,000 households remain evacuated, farmland is contaminated, and radioactive water continues to be a long-term challenge. The flooding disabled electrical system responsible for cooling the reactors. Without the cooling, temperatures rose rapidly, leading to core damage and hydrogen explosions in multiple units over several days. So this picture shows here we have unit 3, 2, and 1. These are the only units that were active during this time, as units 5, 6, and 4 were under repairs. So at 2:46 p.m. we have the earthquake strike. There's a 9.0 magnitude earthquake that hits off the coast of Japan. So at Fukushima, safety systems immediately activate. Reactors 1, 2, and 3 automatically shut down, and the backup generators start to cool the reactors. The problem is 14-meter tsunami crashes over the seawall, floods the plant, and knocks out all the diesel generators. So then we have the radiation emergency beginning, and Japan declares a nuclear emergency. So here we can have a picture of inside the nuclear reactor. You can see the fuel rods inside here, and you can see how if they're exposed and they don't have the coolant going around, they can heat up. This heat produces steam, produces hydrogen steam, which builds up and the pressure builds up, and that was mainly the cause of the explosions, was the buildup of the hydrogen steam. Basically from the emergency cooling, the water would boil, the fuel rods would just be exposed, and hydrogen gas would blow apart the building. Efforts were made to pump seawater into the reactors as a last resort, despite the risk of corrosion and further contamination of that water. Basically, all 1, 2, and 3 reactors ended up exploding, and radioactive materials were released, and the evacuation zone at the time was expanded to 20 kilometers. Some of the aftermath of the Fukushima incident, workers came out and said that the reactors were 40 years old and they lacked modern safety upgrades, and critical safety systems had not been tested in decades. The disaster caused long-term environmental, health, and social consequences for Japan. And as we see in this picture, it shows the radiation over time and the long-term environmental effects, and just how long the radiation stays in the area. Is nuclear energy worth the risk? It presents advantages and challenges. In theory, it offers a reliable energy source that can significantly reduce our dependence on fossil fuels because it does not release as much CO2 into the atmosphere as fossil fuel combustion does. But at the same time, it requires strict safety measures, responsible waste management, and continuous improvement in our technology and regulation. As we look towards the future focused on sustainability and climate responsibility, nuclear power deserves careful consideration rather than immediate dismissal. Thank you for listening, and I would be happy to answer any questions.